No one knew how to build it. That is not a dramatic opening. It is a historical fact. In 1418, the city of Florence announced a competition, open to any architect or engineer in Europe, to solve a problem that had been sitting unsolved for over 100 years. How do you close the largest dome ever attempted in the Western world over a hole in a cathedral ceiling that is 43 meters wide at a height so extreme that standard wooden scaffolding would require more timber than existed in all of Tuscany? The cathedral had been under construction since 1296. The drum, the octagonal base the dome would sit on, had been finished in 1413. And it had been sitting open to the sky ever since, because no one could figure out the next step. The dome was a promise the city of Florence had made to itself, a promise no one knew how to keep. And then a goldsmith with no formal architectural training walked into the competition and told them he could do it. He could not explain exactly how. Not yet. He just knew he could. His name was Filippo Brunelleschi. He was 41 years old, and what he built over the next 16 years is still, 600 years later, the largest masonry dome on Earth. There is a detail buried in how this dome was constructed, a structural secret that Brunelleschi took to his grave and that engineers did not fully understand for centuries after his death. We get to it. But first, the problem. Florence, 1418. The city smells like hot stone and river water from the Arno, wool dye from the workshops nearby, wood smoke drifting from the glazier's furnaces. It is summer, and the heat in Florence in summer does not feel like weather. It feels like something the city is doing deliberately. Walk to the cathedral, stand inside it at the base of the drum, and look up. No painting, no fresco, no dome. Just an octagonal hole in the sky, 43 meters across, open to whatever the weather decides to send down. Pigeons nest along the rim. When it rains inside the cathedral. It has been this way for 5 years, since the drum was finished and the builders ran out of answers. The edge of that opening is 54 meters above the floor where you are standing. The top of the finished lantern, whenever that day comes, will be over 100 meters up. On a clear morning, you can see the drum from the hills surrounding Florence, this great unfinished collar of marble and stone, waiting. The whole city is waiting. This is what the competition is asking someone to build. The standard solution for doming a large space in 1418 was a wooden centering, a temporary scaffold built in the shape of the dome, on which the stone or brick could be laid until the structure became self-supporting. The Pantheon in Rome, the great model everyone was looking at, had been built this way, with an oculus at the top to let the weight distribute. The problem at Florence was the span, 43 meters across. The wooden centering required to support a dome of that diameter would have to rise from the floor of the cathedral, 54 meters below, or be cantilevered from the drum walls in a way that had never been done. Either way, the quantity of timber needed was staggering, and the cost was more than the city's construction budget. Brunelleschi's proposal was simple to state and almost incomprehensible to imagine. Build the dome without centering, without any internal wooden support structure at all. Every other architect who heard this said it was impossible. You cannot lay brick in a curve without something to hold it in place while the mortar sets. Gravity does not wait for mortar. Brunelleschi said he knew a way. He refused to explain it in detail. His reasoning was practical. He did not want his method stolen. He had already been robbed of credit for work once before, during a competition for the baptistry doors in 1401, and the wound had not healed. The city of Florence gave him the contract, partly because his proposal was the only one that addressed the centering problem, and partly because the other architects had run out of answers. The work begins in 1420. And from the very first course of brick, it is clear that Brunelleschi is doing something no one has seen before. He is building the dome in two shells, an inner shell and an outer shell, separated by a gap wide enough to walk through, connected by a framework of stone ribs and brick rings that tie the two surfaces together into a single structural system. The inner shell carries the primary load. The outer shell, lighter and more steeply pointed, protects it from weather and creates the dramatic silhouette that rises above the Florence skyline. Between the two shells, hidden from both inside and outside the cathedral, there are staircases, maintenance corridors, the structural skeleton of the entire dome. This double-shell system was not invented by Brunelleschi out of nowhere. He had spent years studying Roman ruins, the Pantheon, the baths, the vaults of ancient structures, looking for principles that medieval builders had forgotten or never learned. He found them in the geometry of the Roman arch and in the properties of brick under compression. But what he did with those principles was new. Here is the detail that engineers found baffling for generations. The dome of the Florence Cathedral has no tension ring at its base. Every dome that carries significant weight wants to spread at the bottom. The outward thrust, the same force that pushes the walls of a Gothic cathedral apart, acts on the base of a dome the way a boot heel acts on wet clay. It wants to push outward and down. Normally, you contain this with an iron or stone ring around the base of the dome, like a belt holding something compressed. Brunelleschi used chains, iron and wood, embedded in the masonry at intervals as the dome rose. He also used the geometry of the pointed profile. A dome that is taller and more pointed than a hemisphere deflects its own weight more directly downward, reducing the lateral thrust. The dome of Florence is not hemispherical. It is a pointed arch, rotated around a vertical axis. And that shape is not aesthetic, it is structural. But here is what even that does not fully explain. The dome was built without any internal centering at all. Brick after brick, course after course, I laid at an increasing angle from the vertical as the dome curved inward toward the oculus, and nothing underneath to catch them if the mortar gave way before it set. How do you lay a brick in mid-air, at an angle, while 60 meters off the ground, and keep it from falling? Think about what that question actually means. You are a bricklayer. You are standing on a plank of scaffolding suspended from the dome above you over empty space. Below, the cathedral floor is the size of a postage stamp. The brick in your hands weighs several kilograms. You are not laying it flat. You are laying it at an angle because the dome is curving inward above you, and the angle gets steeper with every course you complete. And the mortar under the previous course is still fresh. If the mortar gives before it sets, the brick slides. If enough bricks slide, the course fails. If the course fails, everything above it comes with it. This is the problem Brunelleschi solved with what he called spina pesce, herringbone in English, fish spine, the standard way to lay brick, each one running parallel to the curve of the wall, leaves the joints between them under tension as the dome steepens. Tension is the weakness of mortar. Mortar bears compression well and fails under pulling force. As the angle increases, every brick wants to slide downward along its joints, held only by mortar that has not yet cured. Brunelleschi's solution was to rotate one brick in every sequence 90 degrees, perpendicular to the surface of the dome, pointing inward like a tooth set against the grain. This brick catches the tendency of its neighbors to slide. Instead of a tension failure, you get a compression lock. The bricks press against each other rather than pulling away. Every course, as soon as it is laid, becomes structurally self-supporting. The mortar can take all the time it needs. The bricks are not going anywhere. No centering needed, not because gravity was defeated, because the bricks were arranged so that gravity itself held them in place. Modern engineers who modeled this in the late 20th century using finite element analysis, the most sophisticated structural modeling tool available, confirmed that Brunelleschi's approach was correct. They also confirmed that no one in 1420 had the mathematical framework to prove it in advance. Brunelleschi knew it would work. He had reasoned it through observation, through physical intuition, through the kind of spatial intelligence that lives in the hands as much as in the mind. But he could not write a formula that explained it. He could not show his work in any language the other architects of his time would have recognized as proof. He just built it and waited to see if it held. Pause on that for a moment. A man lays the first course of an experimental brick pattern at the base of the largest dome ever attempted in a method he cannot prove will work, knowing that if he is wrong, the consequence is not a failed experiment, but a catastrophe witnessed by the entire city of Florence. And he proceeds. This is the detail that engineers find difficult to fully explain. Not that the method works. It clearly works. The dome is still standing. But how a man in 1420, without our tools, without our mathematics, arrived at a solution that our tools have since verified. Now think about what it took to actually put those bricks in place, because solving the structural problem was only half of it. The other half was purely physical, and it was its own kind of impossible. The construction of the Florence Dome required machinery that did not exist when the project started. Brunelleschi invented it. The hoisting systems at Notre Dame, treadwheels, pulleys, hand-wound cables, were adequate for lifting stone to the heights of a Gothic nave. They were not adequate for lifting hundreds of thousands of bricks and tons of sandstone to the top of a dome that crested at over 90 meters. Brunelleschi designed a new machine, a large-scale ox-driven hoist with a reversible gear, meaning it could raise loads on the way up and lower the empty rigging on the way down without stopping the oxen and reversing their direction. This was the first reversible gear mechanism recorded in European engineering history. The machine was so well designed that Leonardo da Vinci sketched it in his notebooks decades after Brunelleschi's death, trying to understand how it worked. He spent pages on it. Brunelleschi also designed a rotating crane, the castello, that could swing heavy loads horizontally to place them precisely at the edge of the dome, and a series of smaller secondary hoists positioned at different levels of the dome's interior for the final placement work. None of these machines existed before this project. All of them were invented because the project demanded them. But even with the machines, the physical reality of building the Florence Dome was brutal. The workers lived on the dome. At the peak of construction, hundreds of men were working at heights where climbing down for lunch meant losing an hour of productivity each way. Brunelleschi built canteens on the scaffolding, places where workers could eat and rest without descending. He negotiated with the city to have wine sold on the work platforms, partly because the water supply at height was unreliable, and partly because men working at extreme altitude in the heat of a Florentine summer needed something to keep them functional. The scaffolding he designed was not attached to the cathedral walls. It was suspended from the dome itself, cantilevered outward, hanging over empty space, supporting men laying the bricks that would eventually make the scaffolding unnecessary. Falls happened. The construction records note them the same way they note a delayed brick delivery or a shortage of lime. A few words, a name sometimes. Then the next line of ledger. These men spent 16 years at heights most people never reach in a lifetime, building something they could not stand back and see from where they were working, following instructions from a man who could not entirely explain why those instructions were correct. They trusted him, or they needed the work, or they had been doing it long enough that stopping felt stranger than continuing. Probably all three. Here is a detail that puts the whole project in a different light. At the peak of construction, Brunelleschi and his co-superintendent Lorenzo Ghiberti, the same man who had beaten him in the baptistry door competition 2 decades earlier, came into open conflict over the direction of the work. Brunelleschi had kept the full technical details of his method to himself. Ghiberti, who held an equal supervisory role, did not know enough about the structural system to oversee it effectively. The tension between them was constant. At one point, Brunelleschi feigned serious illness and withdrew from the site for weeks. The construction slowed almost to a halt. Workers and officials came to his house asking what to do. He refused to answer until Ghiberti's authority over the technical decisions was formally reduced. The city complied. Brunelleschi returned to the site. The dome continued. It was not a noble moment. It was a bureaucratic power struggle waged by a middle-aged man in a Florence apartment, using the vulnerability of an unfinished dome as leverage. But it worked, and it was probably necessary. The technical complexity of the herringbone system and the double-shell structure could not have survived divided command from someone who did not understand the reasoning behind every decision. The dome was completed in 1436, 16 years after the first brick was laid. Pope Eugenius IV consecrated the cathedral on March 25th of that year. The building that had been under construction since 1296, 140 years, was finally finished. Brunelleschi died 10 years later in 1446. He is buried inside the cathedral, one of only a handful of people in Florentine history to be given that honor. His epitaph, written by the humanist scholar Carlo Marsupini, calls him a man of divine genius. The word used in Latin is ingenio, closer to ingenuity than to genius. The ingenuity of a mind that could see solutions in 3 dimensions before they existed in the world. Stand inside the Florence Cathedral today and look up. Take your time with it. This is not a space that gives itself up quickly. The interior of the dome is painted with Vasari's fresco of the Last Judgment, a vast, swirling composition added a century after Brunelleschi's death, which he could not have imagined and might not have approved of. But behind the paint, the structure is his. Every visitor who has ever stood here has been inside Brunelleschi's calculation, whether they knew it or not. The 2 shells, the herringbone courses. The stone ribs rising from the 8 corners of the octagonal drum, converging at the oculus 114 feet above the floor. That structure is not maintained by anything that was not here on the day it was completed. No reinforcement added later. No intervention required to keep it standing. The dome holds the way Brunelleschi calculated it would hold, by the arrangement of its own mass, by the geometry of a pointed arch, by bricks laid in a pattern that converts gravity from an enemy into a collaborator. 600 years. In 1420, every expert in Europe said it could not be done. In 1436, it was done. Not because Brunelleschi proved them wrong with mathematics, because he built it course by course, brick by brick, at the edge of what anyone understood, and because the men who carried those bricks to 90 meters and placed them where he told them to place them showed up every morning and did what the work required. They did not know if it would hold. They kept going anyway. The dome did not fall then. It has not fallen since.